So one way we can find if vectors are linearly independent is setting them up as a linear combination, finding all of our coefficients. If they're all equal to 0, they're independent. If they're not equal to 0, they are dependent. Another way to do it, which personally I think is easier, is to find the rank of a matrix. The rank of a matrix is the maximum number of linearly independent rows or columns in your matrix. So essentially what we do is we are going to put all of our vectors in a matrix. You can make them rows or columns, it doesn't matter. And the rank is determined by reducing it to row echelon form. The number of non-zero rows in row echelon form is the rank of the matrix. And it tells us directly the number of linearly independent or vectors in our matrix. And there's a rank function in MATLAB that you can use. So, given a set of vectors, create a matrix. The vectors can be rows or columns, it doesn't matter. Use row operations to reduce the matrix to REF till we have our lower triangle of zeros. And you're going to end up with either something that looks like this, hold on. You're going to end up with something like this. You might end up with something like this. You might end up with something like this. So get your lower triangle of zeros. However many other zeros happen, that's fine. The number of non-zero rows ends up being the rank of the matrix, ends up being the number of linearly independent vectors there are in that set. So here, I have 2 zero rows, which means I have one of these vectors is linearly independent. The other 2 are just repeated information from this first one. And depending on what that rank is, tells us some information about our system. So if the rank equals the number of rows, the vectors are linearly independent. So if I have a rank of 3, then they're all linearly independent in this example, because there's 3 vectors. If the rank is less than that, then they're linearly dependent. So this comes into play when it comes to solving our systems. So given a linear system, AX equals B, we write it in matrix form. We can put it in augmented matrix, and we can perform Gauss elimination. Essentially, we're just doing row operations until we find REF, which is Gauss elimination. Which means we're going to end up with some situations. We could end up with something like this, which is what you've seen previously, where we have 3 equations we can pull out of here, which means that the rank of A, this side, equals the rank of AB, the whole thing. Where the rank of A is 3, because I have 3 non-zero rows. The rank of AB, the whole thing, is also 3, because I have 3 non-zero rows, which means I have a unique solution. We also might end up with something like this, where here, rank of A, if I look at this side here, is 2, because I have 2 non-zero rows. If I look at the rank of AB, I have 2 non-zero rows as well. So this is an instance where I have an infinite number of solutions, where I only have 2 unique, 2 independent pieces of information, 2 independent equations, but I can still write it with an infinite number of solutions, where we saw this before, and we'll go over an example in class. You also might end up with a situation like this, where if you look at the rank of A, it's 2. If you look at the rank of AB, it's 3. Those 2 aren't the same, which means this last equation here tells me that 0 equals 2. That's not possible. So this is an example of where I have conflicting information, where I might have an inconsistent system with no solution. 0 can't equal to 2. You just can't do that. Math defies the logic of math. It defies the rules of math. So this is an example where we have 0 solutions. So the rank is just essentially doing Gauss elimination. However many zeros we end up after we get our lower column of zeros, or our lower triangle of zeros, however many zeros we end up with is fine. That's how it works out. It's just how are we going to interpret the final result. And we can do this on a and AB, do it together. Saves time because it's the same operations. And we can use that to indicate what kind of system we have. Is it consistent or inconsistent, and how many solutions we have? 1, infinite, or 0.